Superfocus CFTs.
Okay. Thank you. So I should start by thanking Fernando and Simone for covering a lot of the material I should be saying things about beforehand, so I don't want to expand too much. But what I want to do is talk about some developments in trying to extend the SYK model, which is a one-dimensional quantum mechanics, to two dimensions. Essentially, the idea here is I want to build a model in two dimensions that exhibits all the nice properties of SYK, or as much of the nice properties of SYK as we can muster up in these theories. And I said, as we ended off yesterday, that that if you try to do this with just a straight-up fermionic model, that at best the interactions are going to be marginal, and if you include higher Q interactions, they're going to be irrelevant. The bosonic models, as I claimed, was either unstable or they didn't find the correct SYK type physics in the fixed point in the IR. So the kind of Goldilocks model where things work out just right, sort of, with some caveats, is actually a supersymmetric theory. So this is the action from the model. I don't want to actually go the usual route of writing down equations of motion and trying to solve this to say that I'm going to solve the theory. I want to use the techniques that Fernando has been telling you about in more generality, in one dimension and in two dimensions. And in particular in this two-dimensional supersymmetric theory, to write down things as generally as I can. In particular, the aim today is to get to the 4-point functions. Once we know what the 4-point functions are, then we can do a whole bunch of things with them. So for example, we can do analytic continuation, and we can study time-ordered correlation functions, and then we can say things about chaos and things like that. I won't do that, but I want to try to write down integral representations for the 4-point functions. That is to say, I don't even want to solve differential equations, if I can possibly help. So to do that, we need some tools. And the first thing that I want to talk about is superconformal symmetry in, we'll start off with d equals 1. And I'm going to remind you of some facts about superconformal symmetry in d equals 1 in a way that's portable to high dimension, in particular d equals 2. So the conformal group in one space-time dimension we've heard a lot about in the last couple of lectures is just SL2R. So we can extend the conformal group SL to R to the superconformal group OSP 1/2 in one dimension. So this is the superconformal group. And d equals 1. By the addition of two fermionic generators. So we'll call them G plus minus half. And these satisfy, together with the generators of SL2R, which I'm going to call L naught and L plus minus 1, these satisfy the following algebra. Commutator of Lm with Ln is m minus n Lm plus n. The anti-commutator, because these are the fermionic generators, of G R with GS is 2 L R plus S and the commutator between Lm with G plus or minus a half is M over 2 minus plus a half G M plus or minus a half. So together these guys form the algebra OSP 1/2. Okay. So far nothing new, but much of what I'm going to be saying here is not really concerned with the algebra, with analysis. So I want to write down differential equations, and I want to try and avoid solving the differential equation, but we at least want to write down some differential equations. So one way to realize this algebra is by acting on some one-dimensional superspace of functions, let's say phi of, to keep the notation consistent with SYK, we'll call them t and theta. Right? So I want to act on, so we can realize the algebra by acting on the superspace of functions t, phi of t and theta, with the following differential operators. So this is now a differential operator representation of these, differential operator representation of these generators that will generate the same algebra. Okay. So L naught is minus t d by dt minus 1/2 theta d by d theta minus delta, where delta is the conformal dimension of phi. L minus 1 is simply minus d by dt. L plus 1 is minus t squared dt minus t theta d theta minus 2 delta t. G minus a half is d theta minus theta dt, and G plus a half is t d theta minus t theta dt minus 2 delta t. So everything we're going to be talking about in trying to understand this conformal algebra will involve these operators, and now they act on these functions and various things that you can construct from them. One thing you could consider constructing from them is the quadratic Casimir of OSP 1/2. So let's do that, because essentially most of what we're going to be doing is looking for eigenfunctions of this Casimir operator. So the quadratic Casimir of course the operator which commutes with all the other generators. And this guy, C, is L naught squared minus 1/2 of the anti-commutator of L minus 1 with L plus 1 minus 1/4 of the commutator of G minus a half with G plus a half. Okay, so we're going to study this guy, and in particular, this is the one particle Casimir. We're going to study the two particle Casimir and its eigenfunctions and eigenvalues. We're going to use that to build up a story, which we're going to then translate into trying to extract integral representations of the correlation functions. Okay, so yeah.
Just a question. If you start with a primary by dt equal to 0, then you start with function which is the identity, and then the rest is polynomials and data, right?
Yes.
And that gives a irreducible representation of the answer, right?
Yes.
Okay, so am I supposed to think of delta as another object that's kind of...
Just acts multiplicatively.
Well, on that representation, yes, but I would expect that the quadratic Casimir is just going to be a number because it's an irreducible representation.
Good. So the quadratic Casimir then evaluates to delta squared minus a half delta in this case. And you should compare that, for example, okay, so that was the next thing I was going to write down. Thanks, Dave. So this is delta squared minus a half delta.
So that's when acting on phi.
Correct. In this superconformal case. And you should compare this with what would happen, for example, if you took just the bosonic case, and you can compare what I'm going to say here with what you would find in, for example, Stanford, Mandelstam and Stanford. There, you would just find that in the bosonic case, it would work out to be delta squared minus delta for strictly bosonic case. Okay. So that factor of a half is important in some of the things that follow. So, in general, we're going to need to understand what happens with the two-particle Casimir, which I'm going to label by C12. And basically what this tells me is that everywhere you see an L, you have an L1 plus L2, square that. Same with the G's. Okay. So then you'll write down, so this is a differential operator. Okay. So then you'll write down some elaborate differential operator for this two-particle Casimir. And what we want to do is try and understand how, well, we'd like to write down the Casimir differential equation and solve it. So the two-particle Casimir, for a two-particle system with coordinates, let's say T1 theta 1 and T2 theta 2. This guy acts on some function, and just to make things simple to write down, I'm going to set delta equal to 0 and write down these expressions. If you want the answer for general delta, you can always conjugate by T1 minus T2 minus theta 1 theta 2 to the 2 delta. Okay. So C12, which is the two-particle Casimir, acts on some function phi of T1 theta 1, T2 theta 2. I'll write down this horrible expression just once and I won't come back to it. So T12, which is T1 minus T2, minus quarter, yeah, it's just C12. Minus a quarter theta 1 theta 2 squared d1 d2, meaning d by dt.
So Jeff, you said 1/4 and now we wrote 1/2, so is it 1/4?
Oh yeah, sorry. 1/4. Phi plus half T1 2 minus T1 2 phi. Sorry.
Jeff, why is it C12 and because I thought C was just the number, so what is C12?
A differential operator. So it acts on phi for reason. Okay. So right now I'm just telling you what the action of C12 on this phi is. Okay. So that's d theta 1 d theta 2 phi plus T1 2 times theta 2 minus half theta 1 d theta 2 d1 phi, and then finally minus T12 theta 1 minus half theta 2 So again, I've set delta equal to 0 in writing this, but you can conjugate by T1 minus T2 minus theta1, theta2, to delta if you want the modular number expression. We won't need it in the workflow. So pretty much what I want to focus on right now will derive essentially from the normalized 4-point function of the theory. So that's what we're trying to aim for in the rest of the talk. For some 4-particle system with coordinates, let's say theta1, theta2, all the way through to theta t4, theta4. The 4-point function has a certain set of properties. A certain set of properties, well, two of them that are important for us is that it must be a superconformally invariant function of the theta I ti's, and that it must be Grassmann even. So those are the two properties that we're going to rely on most forms. Those two properties themselves, the fact that it must be superconformally invariant, as well as Grassmann even, tell us that this thing can only depend on the two, in this case, Grassmann even superconformal invariants. So you already learned from Fernando and also from Simone this morning about the conformal cross ratio. So together with the conformal cross ratio, there's one nilpotent invariant, and those are the only two superconformally invariant variables, Grassmann even variables, that the 4-point function is going to be a function of. So let's write them down. We're going to need them in a little bit. So I'm going to call the one chi as well. This is the standard thing to do. It's not the same chi as what when I wrote down. It's a superconformal. It's a super analog of it. Okay, so in this case, chi is, let's say, 1, 2, 3, 4 divided by 1, 3, 2, 4 minus zeta. So this combination, let's say I, comma j, is just the notation that we'll use to define t I minus t j minus theta I theta j. Okay, so if you set all the Grassmann, if you set all the thetas to 0, you'll find that this chi reduces to the conformal cross ratio that you've read about before. And zeta is the second one. And this is 1, 2, 3, 4 plus 1, 2, 3, 1, 4 plus 3, 1, 2, 4, all divided by 1, 3, 2, 4. This guy is nilpotent in the sense that, well, in the usual sense that zeta squared is 0. And you can check again that if you turn off all the thetas, this guy is identically 0 for the bosonic case. This combination here cancels out the pairs. And one way to check that it's nilpotent is to use the OSP 1/2 to fix 3 of the bosonic coordinates and 2 of the fermionic coordinates, in which case this guy is just bilinear in the thetas, and you square it and it's 0. Okay. So the 4-point function that we're looking for is an eigenfunction of this 2-particle Casimir operator. So now all we need to know is essentially how this guy acts on functions of these two guys. They're not any old functions, they're functions that can occur in only a specific combination. So all we need to know is how does C12 as an operator.
Sorry,
Yeah.
I ask a maybe silly question compared to higher dimensional conformal field theories. So usually when we take an operator phi and we act with any of the conformal generators, we get a descendant. So like the 4-point function is not an eigenfunction by itself,
No.
but it's a sum of eigenfunctions.
Correct.
But here it is an eigenfunction.
Yeah, it is an
Would you like to explain maybe?
I'll get to that in a little bit, and you can see exactly how it will arise, right? So, okay. So, the functions phi that we're interested in acting on are of the form some function just of chi plus zeta times some other function just of chi. Okay. And the way, okay, so now we can do this in general, or we can use the OSP1/2 that we have at our disposal to fix some things and make our lives easier. So we're going to do the following. We're going to fix, again, this is just a matter of convenience. We're going to fix T3, T1, T4. We'll set out to infinity, and we'll turn off theta 3 and theta 4. So that in this case, chi is just T12 divided by T1 minus 1. And zeta is just theta 1, theta 2 divided by 1 minus T1. That simplifies the action of C12 quite considerably. So let me show you what that comes out to. Then we need to say a little bit about various real analysis kind of things.
So for the time being, all what you are saying is true for any function phi of chi and zeta.
Correct. Okay, so now let's do the following. Okay, once we've fixed these values of t and theta, so that chi and zeta take the following form, then the action of C12 on functions of this form is quite simple. It acts as follows. C12 acts on phi as, let's write it in a matrix form. So this D is going to be a 2x2 second order differential operator, okay, acting on a vector f of chi and g of chi, where D has the following form. And when I write this down, you recognize some of the components, and you'll see how this is going to piece together with the usual way of thinking about, well, with the bosonic case. So the 1, component is chi squared times 1 minus chi, d chi squared minus chi squared d chi. Then there's chi over 2 times 1 minus chi, d chi squared minus chi over 2 d chi. Chi squared times 1 minus chi, d chi squared, plus chi times 2 minus 3 chi minus chi plus a half, and top here is just chi over 2. So this is a 2 by 2 matrix of differential operators. There's a bunch of things that you need to think about when you're working with a differential, with an eigenvalue problem like this. One is because we need to use theorems from linear algebra about the basis of eigenfunctions, whether it's complete, etc. We need to understand whether this thing is Hermitian or not. Hermitian in the sense that Fernando talked about yesterday. So what we would like to know is whether this operator, as a differential operator, is Hermitian. Turns out it is not Hermitian with respect to any positive definite inner product. So we need to say a little bit about measures that we're going to use to determine the inner products with respect to which this guy is positive. Because once you have a positive definite operator, then you can be sure that the basis of eigenfunctions that you're going to construct is going to be sufficient for what you need. I'm not talking about boundary conditions at the moment. They are as problematic here as they are in higher dimensions. But we're going to evade a lot of that by going to the integral representations. Okay? So let's make a note that this guy is not obviously Hermitian with respect to any positive definite inner product. So let's say a few words about inner products and measures. So the first thing to do is let's talk about SYK in one dimension. So in particular, I want to go back to the Mandelstam Stanford paper. In D equals 1 SYK in the Mandelstam Stanford paper, they come across a similar kind of story. They're looking for eigenfunctions of the two-particle Casimir. In this case, the two-particle Casimir operator looks as follows. And I'm going to distinguish that case from the super Casimir that we have here by curly C. So C1, 2. And this guy acts on functions of T1 and T2. Everything's taking place on a line. And the action of this, as you reminded me this morning, is minus T1 2 squared dt1 dt2 f acting on T1, sorry, acting on T1 f of T1 T2. Well, this guy is Hermitian with respect to an inner product, and the inner product is that f so this is Hermitian with respect to the following inner product. F inner product G is the integral over T1, T2 divided by T1, 2 squared, F star G. Okay? So, of course, here as well, we want this to be a function of the conformal invariant. So you can write it in terms of the conformal cross ratio. This time I do mean the chi that we read about earlier. And this is the integral over chi squared, f now function of chi star g. But then you should ask about limits of the integral. Well, here, the integral goes from minus infinity to infinity. Sorry, this is time, so it goes from 0 to infinity in both cases. And here you would expect that the integral goes from 0 to infinity as well. However, S1k has a particular symmetry. The symmetry is under chi going to chi over chi minus 1. And in anticipation of the symmetry, you need only do the integral from 0 to 2, which is the fundamental domain. Okay, so now we understand what the inner product is with respect to which the two-particle Casimir is Hermitian. And then if you read the Mandelstam Stanford paper, they spend the next 5 pages or so elaborating on the solutions, the boundary conditions, etc., etc. And then the reason these things are important is because they feed directly into the construction of the correlation functions. Okay, so this is what happens in D equals 1. What about in the super case? Well, in the super case, the natural extension, just following intuitively, the natural extension of this inner product should be we'll take A inner product B to be the integral now taken over T1, T2, theta 2, theta 1 divided by 1, 2, AB. So there's a couple of things to note here. One is I should tell you how I'm doing my Grassmann integrals, how I'm normalizing my Grassmann integrals. The Grassmann integrals here are normalized as follows. If I take the integral d theta 2, theta 1, theta 1, theta 2, that's 1. This guy is the same as this. And the reason why I have this is because now if I make sure that A and B are not functions of the thetas, and I do the Grassmann integral, it comes down to exactly what Mandelstam and Stanford had. So if I integrate out the thetas, I recover the standard case. Okay. There's also one point to notice is that there's no star here. It's not a typo. Essentially, this is not positive definite in any event, and so we take it to be just defined as bilinear in the product instead of Hermitian.
Sorry, may I ask a really silly question? So when you move from T1, T2 to the cross ratios, in order to define a cross ratio, you need 4 particles.
Correct.
And
so I've set
I see.
these guys, but you can recover the story in general.
I see. So really, F is a function of 4 variables where you have set these terms.
Correct. Right. So this is a bilinear inner product. Which will be useful for us because we're going to be dealing with real superfields at the end of the day. I should say that in the action that I wrote down, this was the n equals 1 superfield story. You can generalize this to n equals 2, in which case you're dealing with complex superfields, in which case you can generalize this guy as well, and it comes through perfectly fine. But this will suffice for our purposes. And C12 is Hermitian with respect to this guy in the following sense. If I take some A of theta 1, theta 2, sorry, T1, theta 1, T2, theta 2, inner product with C1, 2, acting on B of T1, theta 1, T2, theta 2. Then this is the same as C. 1, 2 acting on A inner product. That's what I mean when I say it's Hermitian with respect to this particular inner product. Of course, as Fernando told you, to check hermeticity, effectively, all you're doing is integrating by parts. Every time you integrate by parts, there's boundary terms that you need to be careful about. I'm not going to be careful about those boundary terms right now. It does work out. You can check that it does. Of course, these boundary terms are important in defining boundary conditions that you're going to be using to solve the differential equation. Okay. It would also be useful to write down this inner product in terms of the superconformal invariance. So in that case, I do the following. Firstly, I need to reintroduce T3, theta 3, T4, theta 4. And then I'm going to restrict the functions A and B to be functions of chi and zeta in those cases. And then I'm going to gauge fix using the OSP 1/2 action by fixing 3 points on the line. So we'll set T1 equal to 0, T3 equal to 1. T4 to infinity, and we'll turn off again the theta 3 and theta 4. So in that case, I can write this guy as minus the integral d chi d zeta over chi plus zeta, and A now a function of chi and zeta, B a function of chi zeta. Okay, so again you should ask me questions about the limits of the integral. So, of course, this integral really means two things. It means integrate over chi and zeta. But I can use the same symmetry properties that we saw in SYK, which restricted you to the integration over the fundamental domain of chi, to do something similar here. In this case, it's worth noting that in terms of these superconformal invariants, this what will effectively be this supersymmetric SYK model has the symmetry has a symmetry under the exchange of particles 1 and 2 and particles 3 and 4. This manifests in the following way. It tells you that it should be symmetric under chi going to chi over chi minus 1. This was the same as we saw with the SYK model. And zeta going to zeta over chi minus 1. And this is the statement that the theory ought to be symmetric if you exchange particles 1 and 2 or
Yeah. Why do you say that is no positive? You just constructed one, no?
Permission. So I constructed a bilinear. I constructed a bilinear one.
Here, what was that? Louis.
This one? This one?
Yes, yes.
Yeah. So if I put a star here, then it wouldn't work. It's not positive.
But your functions are here. You're looking at your functions like that. Good stuff. Is it so? Like the hypergeometric function, I guess.
That's correct.
And real, I guess. Okay, but anyway,
That's correct. That's
that's just the language. Doesn't matter to you, you define an eigenvalue which would be real, no?
That's right.
Okay.
And I can check that the basis is complete as well. Okay. All right, so
Sorry,
yeah,
I missed a few words of what you two were discussing. So you will have an eigenvalue problem. This eigenvalue problem will have real eigenvalues because this is a Hermitian operator. And the question is whether these are positive or real is good for you.
real is good for me.
Then,
Okay. Okay, so let me make some comments quickly. Firstly, this has to be symmetric under this change in chi and zeta. And if I look at a function like this, for example, then this function is symmetric under, is invariant under this particle exchange if g goes like chi minus 1 times g under this. The derivatives change in a particular way when I make this change of variables. That, together with the way g transforms to make sure that this guy is invariant, tells me that d, this d, is also invariant. Okay. It's a small exercise, but you can check that that's the case. All right, so now I want to return to this eigenvalue problem that we're trying to solve.
so you don't expect to have a symmetry exchanging 1 and 3 that would take chi to 1 minus chi or something.
There's a separate symmetry there, and I'll comment on that. But no, I don't expect that. So if we go back to our eigenvalue problem, we had D acting on this F and G equal to H times H minus a half. H times H minus a half acting on F and G. So this is an anticipation of the fact that I know what my eigenvalue should look like. This is the Casimir for two particles coupled to a dimension H prime ring. This is the form of the eigenvalue problem, and this is what I want to try and solve. Again, this is two coupled differential equations, ordinary differential equations in chi like this, but two coupled second order differential equations. So to solve this eigenvalue problem, you can do the following. We'll take as an ansatz that g of chi is h over chi times f of chi. It seems like it's just coming out of thin air, but it's not. I'm going to show you when we go to the shadow representation for constructing 4-point functions that this ansatz comes out quite naturally in the integral representation. But for now, let's just see where this takes us. Okay, so I'm going to set g equal to h over chi times f of chi, and that decouples these two equations. They actually turn out to be both the same equation, so I need only solve one of them. And with this, let's just solve the equation for f, say. The eigenvalue equation becomes chi squared times 1 minus chi d2f by d chi squared minus chi squared df by d chi minus h times h minus 1 times f equals 0. So let me ask the students, what's that equation? Anybody recognize that equation? Yes?
Looks like a Bernoulli type equation.
It's like a Benedita equation. We have one taker. That's usually my way of saying no. So think about the functions that we've been hearing about in this.
Hypergeometric.
There we go. So this is a hypergeometric equation. And there you go. This is exactly what we've been hearing about in the last couple of days. This is just the hypergeometric equation. So the Casimir differential equation is the hypergeometric equation, and we should expect hypergeometric functions as solutions of the hypergeometric equation. There are two linearly independent solutions, as you would expect for a second order differential equation. These are the following. So the solutions of this equation, the general solution of this equation is that f of chi is some c1, little c1, chi to the h times the hypergeometric function 2f1 of h, 2h, chi. So this you would recognize from what someone wrote down this morning, plus a linearly independent solution chi to the 1 minus h, 2f1, now of 1 minus h, 2 minus 2h, that's the function of chi. So we should check that this satisfies, well, that this is consistent. Right. So the first thing is, we started off with a 2x2 system, so we have two hypergeometric equations, more or less, right, in two functions. And we get two solutions from here. So the counting doesn't quite seem right. I need 4 linearly independent functions. I get 2 from this guy. But actually, we noticed that the eigenvalue problem, this eigenvalue problem, is invariant if I replace h with a half minus h. So in my ansatz, I could have taken, instead of taking h over chi times f, I could have taken a completely independent ansatz of a half minus h over chi times f, and I would have gotten 2 more solutions. So those 2 solutions plus these 2 solutions, and the counting comes up right. I have 4 linearly independent functions that solve the eigenvalue problem. Okay. So now, among how much time do I have? 12 minutes. Okay. So now, if I can get to the shadow formalism, that would be great. But at this point, I have the general solution. I need to figure out how to restrict these guys, and to restrict these guys, I'm going to go back to the differential equation and tell you about boundary conditions. Then I specify the boundary conditions, and there's some subset of these solutions that will serve the purpose that we need to do. But we're not going to do that. I don't want to have to solve the differential equation. Instead, I want to think about another way of constructing the 4-point functions without solving the differential equation. So if you've had to plug your way through Moss and Feshbach at any point, then there's a very powerful method for solving differential equations that actually involves not solving the differential equations, but writing down integral representations. Sometimes you can do those integrals, and when you can do those integrals, then they will form these functions. But actually the integral representation is far more powerful, and it's also more general in the sense that you can generate a whole bunch of solutions to differential equations. Again, without solving the differential equation. So the differential equation that we have in mind is the Casimir differential equation. This is the super Casimir differential equation, because it came from this problem here. We then want to extend this to 2 dimensions and to 2-dimensional superspace. So it's going to get a little more complicated as we go along, but the principle applies and it stays the same. So this is why I want to think about it in this way. So let's very quickly introduce the shadow formalism, and then I want to revisit the SYK model that we spoke about yesterday and show how the properties of the SYK model come out quite naturally in this formalism. So for anyone familiar with conformal field theory, the shadow formalism is actually not new at all. It goes back to the 1970s and the Italian school of conformal field theory, where they wrote this. They wrote these this construction method out. And then it was resurrected again by Osborne and Dolan in their paper on partial wave expansions. And now it's resurfaced again with vengeance in the context of bootstrap program, and specifically the analytic bootstrap. Okay. The shadow formalism, shadow construction, is a technique that allows us to construct the 4-point function of conformal field theory for some specified value of the conformal Casimir, without solving the Casimir eigenvalue problem. So, the first thing to note is that we want to solve, or we want the following object. So we want some operator O of x1, O of x2, O prime of x3, O prime of x4. And what we want to do is calculate the connected 4-point function of this guy. So this is the connected 4-point function. And these guys are dimension delta conformal primaries in, let's say, d dimensions. So these are dimension delta primaries in d dimensions. So this is what we want. This is the 4-point function. If we can write down a representation for this 4-point function, or if we can, even better, just write down the 4-point function, then we can do all sorts of things with it. Right? So what we're going to try and do is get an integral representation for this 4-point function. I just want to write it down in terms of some integral. Might not be able to do that integral, don't care. Most of the properties will follow from the integral itself. Okay, so the strategy is the following. The shadow formalism says, think of O and O prime as living in two separate decoupled CFTs. Let's call them CFT1 and CFT2. CFT2 is what we would call the shadow CFT. It is in some sense auxiliary to this problem. Okay. So point 1 is O and O prime live in two decoupled CFTs. In, let's say, d dimensions. So I don't need to specify this right now. I'll do it in a little bit when we set d to 1. Go back to the SY. In addition, I'm going to assume that living in these CFTs, I have some conformal dimension H operator that lives in CFT1. And I have another one, let's call it V prime. And this has complementary dimension D minus H, and it lives in CFT2. So now if I go ahead and calculate, because these are decoupled CFTs, if I go ahead and calculate the connected 4-point function for this guy, it's going to be 0. But I can perturb the CFT by some operator. I'll write down what that operator is. And that will allow me to write down a resolution of the identity, which I can then use to generate a 4-point function that is non-zero. So strategy 3 is perturb by some operator that's epsilon. Maybe I should change epsilon dd of y, v of y, v prime of y. So then, this 4-point function that we're looking for, this guy, can just be written as epsilon this feeds back into here, and this is epsilon times the integral over d dimensions times O of x1, O of x2, V of y, all of which live in CFT1. O prime, sorry, not O prime, V prime of y, O prime of x3, O prime of x4. So that's it, and you can see how this is like a resolution of the identity. We've inserted this VV prime in between here, and then we integrate out of a y. And that's it. You have an integral representation for the 4-point function.
But sorry, is that true to first order in epsilon?
Yeah, correct. So these guys, these 3-point functions, are single-valued, conformally invariant eigenfunctions of the two-particle Casimir C12. So these are single-valued, conformally invariant eigenfunctions of C12. So if we can write these guys down, I can immediately construct a 4-point function for you in an integral representation. Now, and this then allows us to construct a basis of functions in which we can expand the 4-point function of, for example, the SYK model. So let's 3 minutes. Excellent. So let's do this for the SYK model. So I'm going to go back to the model we've been talking about yesterday, the one-dimensional SYK model, where we had these fermions. We know what the 2-point function is. We can use this to construct the 3-point function. Once we know what the 3-point function is, we can then write down the 4-point function. So I'm going to tell you which is the contribution that comes to the 4-point function. So let's go back down to d equals 1 now. And SYK. There, we found that psi I of t, psi I, let's say psi j of t prime, where this is now the disorder averaged 2-point function, is delta ij times the sine SGN of t minus t prime divided by mod of t minus t prime to the 2 delta. Okay. The 3-point function. Okay. Right. And the 3-point function psi I of t1, psi I of t2, and v of t3. Now I should say that because these guys are dimension delta fermionic primaries, this guy has to be a dimension H bosonic primary, otherwise it would be 0. Okay? So I have these 2 fermions and a boson, and this is sine of t1 minus t2 divided by mod t1 minus t2 to be 2 delta minus h mod t1 minus y. Sorry, it should be y. T1 minus y to the h, T2 minus y to the h. So then we take this guy, we insert it into the shadow representation, and we find that what we get is a contribution to the normalized 4-point function. So okay, so the normalized 4-point function that we're going to be interested in is one that looks like the following. In fact, let me write it like this. So normally, if I wanted the normalized 4-point function for these fermions, I would write down psi I, T1, psi I, T2, psi j, T3, psi j, T4, divided by psi I of T1, psi I, T2, 2-point function of that, times the 2-point function psi j, T1, psi j, T2, and such.
Sorry, in general, to get the 4-point functions, do you need to sum over h or something like that, or?
Yes, but I'm going to write down just the integral, and and then we're going to read off what the integral is, and you're going to see that it's going to be exactly. We know what the answer is. We just wrote down the answer just above here. It solves the hypergeometric function, so it's got a hypergeometric equation, so it's going to be a hypergeometric function subject to some boundary condition. So hopefully this will end up being that. So let me just show you how that will be in a few minutes I have made. So the problem with this is that while it's conformally invariant, it's not particularly useful in the SYK case, because there we need to do a disorder average, we need to average over labels, we need to remove the identity, we need to remove the contribution from the identity in the 1-2 channel, and we also need to have a well-defined large n limit. So this is not the appropriate 4-point function to consider. Instead, I'm going to put primes here, indicating that when I take the average, I'm doing all of the things that I told you about. Disorder average, average over labels, etc. And then we'll throw in an n here, so that we make sure that we have a well-defined large n limit. And this is the guy we're going to be considering. So let's call this thing f of t1 through to t4. So in the SYK case, this is the normalized 4-point function that we're going to be considering. And in fact, when I said that the shadow formalism generates the contribution to this guy that we're interested in, it's the contribution to this guy. Okay? In particular, the contribution generated by the shadow representation.
Sorry, but to get the physical 4-point function, don't you need to remove the contribution of the shadow? And this gives the sum of the physical block and the shadow block.
Right. So yes, you do. I probably won't have any time to discuss how you do that, and summing over the h's, for example. But yes, you do. Okay. So once you do, the contribution to the 4-point function is half of the integral over y of mod t1 minus t2 to the h mod t3 minus t4 to the 1 minus h mod t1 minus y to the h t2 minus y to the 1 minus h to the h 3 minus y, to 1 minus h, t4 minus y, to the 1 minus h. And my claim is that all of the properties of the 4-point function that we want sit in this integral representation. Okay? And really all you need to know is integral representations of the solutions of this differential equation. So there's a couple of points to note. One is that this integral, well, okay, whenever we do integrals like this, we need to ask questions about when the integral converges or not. So it certainly does converge, and converges when the real part of h is between 0 and 1, but you can analytically continue into the entire complex h plane. However, you'll end up with neuromorphic functions psi. The second thing is that conformal invariance tells us that, again, this guy must be a function of the conformal cross ratio. So this is the statement that psi h is a function of chi only. So we can recast this thing with a little bit of work into that form. Here, y goes from minus infinity to infinity, dy mod chi dh divided by mod y to the h chi minus y to the h 1 minus y to the 1 minus h. And from this representation, basically, we can read off all the properties that we want of the 4-point function in the SYK model just by looking at the integral representation. So for example, we know that SYK has this symmetry under particle exchange, particle 1 and 2 or 3 and 4. Well, in that case, that tells us that chi goes to chi over chi minus 1. And if you study the integral representation, what you'll find is that and I'll finish off this now. What you'll find is that psi h of chi is psi h of chi over chi minus 1. So yes, indeed, this particle exchange symmetry is built into the integral representation. You also find that if you exchange y with chi over y, then psi h of chi is the same as psi 1 minus h of chi. So this you can show by sending y to y over chi, so chi over y. And this is nothing but the statement that psi h is an eigenfunction of C12 with eigenvalue h times 1 minus h, which is invariant under sending h to 1 minus h. So there you go. Psi h is invariant under h going to 1 minus h. And again, you can just read it off from making a change of variable in the integral and rewriting the integral in that form. Okay. So there's various other things that you can do. For example, the OP, if you wanted to understand the OPE for the 4-point function, you need to know the behavior of the 4-point function near chi going to 0, make a Taylor expansion of the integral representation, and you can find that you can write it in terms of trigonometric functions multiplying gamma functions. Right? Exactly because you know what the integral representations for gamma functions are. Basically, you can show that you can write this guy as some coefficient multiplied by the conformal block twice O2R in exactly the same way that you would expect if you approach the problem from solving the Casimir differential equation. So this Casimir, this shadow representation gives you a way of constructing the 4-point function not only in SYK, but also in the supersymmetric version of SYK in 1 dimension, but also in the supersymmetric version of the 2-dimensional problem that we started off wanting to discuss. The formalism goes through exactly the same. You write down an integral representation for the Casimir differential, for the 4-point function, and then once you have that, you can do whatever you want with it. You can analytically continue it, you can study the out-of-time ordered correlation function, where these objects here are not inserted in increasing time, but in out of time order, which then allows you to say things about the chaos regime of the theory, etc. I didn't get anywhere close to where I wanted to go, but I hope that at least I've conveyed to you some of the power of using these modern CFT and bootstrap methods, even in disordered systems. Thank you.
We have time for 1 or 2 quick questions, perhaps. Otherwise, let's postpone that to lunchtime. Thank you. Thanks, Jeff and you.